afternoon. Our first speaker is Bartek Czech, and he will be telling us about query complexity and the cutoffs in ADS3 CFT2. Let's welcome.
Okay. Thank you very much for giving me a venue to speak here. Let me just briefly say that this is work that is based on one paper that already appeared and one that's in progress. The one that appeared was together with Chen Bowen and Wang Zizhi, who are students here at Tsinghua. And the one that will, the future papers that will come on the subject will be in collaboration with Lampros, who spoke earlier today, and with Jan de Boer. So I think that most people will probably be familiar with the subject of complexity. So I don't need to spend a lot of time motivating complexity, but just a brief reminder. We often talk about spatial sizes in the ADS CFT correspondence. And a prime example is if I have a black hole, which I look at spatial slices of that black hole at various times, then I find that they grow. And so there's a question, what is growing if the black hole is growing? And even without the growing part, even if I remove the words growing in this box, there is a question, well, Ryuta Kayanagi, roughly speaking, told me that entanglement is manifested in ADS CFT or in the bulk as surfaces which are codimension 2. But what about objects which are codimension 1 or maybe codimension 0? Their internal volumes, so the volume of a spatial slice, or maybe the volume of a Wheeler-DeWitt patch, a codimension 0 object, what is that? And there should be an answer to that question because these are such compellingly simple objects or quantities from the gravity point of view. And so Lenny Susskind and others around 2015 said that spatial sizes in ADS should be related to state complexity in the CFT. And here I have a comment that this proposed correspondence is, okay, and here I have a reminder to say glass half full, half empty. So I'm about to comment on this proposed correspondence in a typical glass half full, half empty fashion. On the one hand, it is neither side of this thing is well defined. So do we even have a proposal at all? That's the glass half full. In particular, there is no a priori given way of quantifying what we mean by the spatial size in ADS. Do we mean the max volume? Do we mean the action in the Wheeler-DeWitt patch? Maybe we mean something else. And on the state complexity side, things are, I would say, even worse. We really don't have a good notion of what it means to quantify state complexity. There are obviously some proposals out there like circuit complexity or distance in the Fubini study metric. There's also proposals based on path integral optimization. And at some point I wrote one paper in that direction, but it's mostly due to Tadashi Takayanagi. There are also other proposals out there that I am not listing. But the short summary is that both sides of this correspondence are not defined until we come and give a definition. So that seems like a bad thing about this proposal, but that's also a good thing about this proposal because there's still a lot of flexibility and there's a lot of need for creative input for interpreting this proposed correspondence. So my goal today is to give an interpretation of both sides of this box, but I'm not going to, I just want to be clear about the philosophy here. I am not going to be committing to volumes of spatial slices or actions in Wheeler-DeWitt patch, or on the CFT side, circuit complexity or distance in Fubini study metric or anything like that. I just want some measure of complexity, which is defined in the CFT and which is defined, which when I evaluate it, it turns out to quantify somehow spatial sizes in ADS. So that if the spatial sizes are bigger, that quantity is bigger. That's the kind of criterion I'm looking for. Now, if it turns out that my notion of state complexity in the CFT obeys the condition that bigger spatial sizes mean that that quantity is bigger. But it is, the quantity is not volume or action we will do it patch. I will say that I'm happy because I don't care about reproducing these specific proposals. I just want some measure of spatial sizes in ADS, which is faithful in the sense that bigger sizes mean that my quantity will be bigger. So that's one criterion of success that I'm setting up for myself. And the other one is I want this proposal to be well defined on the CFT and well motivated on the CFT side. And so today I will give you such a proposal. Any questions about the philosophy so far? Okay, so first a preliminary. In the title I said complexity and cutoffs. So let me just comment about why cutoffs are so important. No matter how we interpret or define complexity, in a conformal field theory, it will always be infinite without a cutoff. And why is that? Because we're talking about theories which are dual to conformal field theories, and conformal field theories are theories without a scale. That means that all scales in the CFT are on an equal footing. So no matter what complexity means, if I'm going to prepare, let's say, the vacuum state in the CFT, I have to make sure that my preparation is correct over an infinite range of scales because all of them are on equal footing in the CFT. That means that I have to take care over infinitely many details, the details being attached to particular CFT scales. The fact that I have an infinite spectrum of scales in a conformal field theory means that I have infinitely many details to take care of. So complexity can only be infinite unless I impose a cutoff. And so that's the statement here, that without a cutoff state, complexity must be infinite. And it only becomes well-defined and finite after we specify some kind of cutoff. So that's why the cutoff is so important. And now let me again state my plan for today. I will give you a completely new idea, or I think it's completely new, for how to think about state complexity. In fact, I will have to tell you a new idea about a cutoff, and I'll have to go even more basic than that and give you some new idea about what a state is in state complexity. And in going over all these proposals, some of them radically new, some of them just a little new, I think it's important to emphasize what my logical starting points are. So my logical starting points are these. Subregion duality, I'm assuming it to be true. That's the statement that if I only have access to part of the CFT, then I have only access to part of ADS. And the parts are well defined under this subregion duality. The second thing is modular parallel transport. It's a way of mapping entanglement wedges to entanglement wedges, or reduced density matrices in the CFT to other reduced density matrices. In fact, Lampros in his talk today more or less used it when he talked about his modular scrambling modes, which often are generators of modular parallel transport. And then for complexity itself, there is a logical starting point I'll be using, which is a completely different notion of complexity that computer scientists have defined, different from circuit complexity or other types of complexity you might imagine, which is query complexity. And what is that? Well, query complexity is something that applies to algorithms. If I have an algorithm, then I can ask how many times does that algorithm call on a certain subroutine. And so we will think about a state today as a map which takes operators to real numbers, and we will specify this map as an algorithm. And then I will be asking if my state in mapping operators to real numbers, which are their expectation values, if my state is, if I am told to make a certain, to carry out a certain computation, to carry out a certain algorithm, how many times I will be using a certain subroutine in that algorithm. And that is query complexity. So my next goal in the talk is to tell you about how to think about a state as an algorithm. And then the notion of query complexity will become applicable, and then we'll see where we go from there. Are there any questions about that? So if not, but I welcome questions, then let me emphasize this point about a state as a map from operators to expectation values. You give me a state, and then what is a state? Well, we're used to thinking of it as a matrix, but the entries in the matrix, I'm talking about a density matrix, but the entries in that density matrix, if I wanted to pick them out, I would take the matrix elements of that matrix. And what are they? They are expectation values or they are traces of the matrix times some row vector times some column vector times some row vector. Trace of that object is a matrix element. More generally, the density matrix or a state is really defined by the set of expectation values for all possible operators with which I can probe it. And this is a perspective on states which is common in quantum information theory. We routinely in quantum information theory think of a state as a map from operators to real numbers. You give me an operator and I'll tell you what the expectation value of that operator is in my state. And that's what a collection of answers to such questions is what a state is. So we should really think of a state as filling out a table like this. I have a column of all possible operators I could have in the theory. And then on the right-hand side, I just have to give you numbers for what the expectation values are. And if I gave you all the numbers, then I have given you the state. So that's what a state should be. Now, how does a cutoff come to play here? A cutoff, we can imagine that a cutoff separates the set of operators into those which are more coarse-grained and less coarse-grained than the cutoff. So a cutoff would be like a division of the set of operators into two classes, the ones that are sensitive to physics below the cutoff and the ones that are not. And so defining a state at a cutoff means that I should give you these expectation values for all of these operators, which are coarser than the cutoff, but for these ones, I don't have to give any answers. So if you give me an operator, I'm allowed to say, oh, this operator is more UV, it's below the cutoff, so I'm not going to give you an answer to it. I can give you some nonsensical answer, or maybe I won't give you any answer, but I'm not responsible for things here. I'm only responsible for filling out this table for operators that are at the cutoff or coarser. So in that sense, I would say that the cutoff, when we discuss a state, is a statement about the domain of the map from operators to real numbers. For which operators should I really realistically compute expectation values? That's the definition of a cutoff, and we should be applying it together with a definition of state as a map from operators to real numbers in this way. So a cutoff restricts the domain of the map from operators to their expectation values. Now, how exactly do we compute these numbers? So I just told you that a state should be a list of such numbers. Maybe I only have to specify these ones, but in practice, how would I compute them? So the answer that I want to propose is that we always specify a state in the form of an algorithm for computing some answers. So let me explain what I mean by this. Here's the first example, the ground state in a conformal field theory. A ground state is specified by these conditions, that it is annihilated by these free generators. I'm assuming that I'm in a two-dimensional conformal field theory. So these are symmetries of the state, and when you open DiFrancesco or any textbook on conformal field theory, expectation values of operators in that state will be computed by exploiting these symmetries. So you say, whatever the correlation function of two operators of a bilocal operator is, it must have this form because otherwise it would violate these conditions. So this is, in this case, the algorithm for computing correlation functions is based on some special properties of the state, and the properties of the state define for me or suggest for me some reasoning for deducing these correlation functions. So the algorithm is deduced based on the symmetries, basically. That kind of way of getting correlation functions or populating this table, that kind of way works only for states which are very special, which are defined by some kind of symmetries. In other words, if my state has some very peculiar property, then I can take that property to turn that property into a trick for computing correlation functions in that state. It's hard to see how to generalize it to arbitrary states, however. Arbitrary states do not have special properties, or if I identify a special property of any particular state, then that's probably equivalent to computing the correlation functions anyway. So we need some more robust way of thinking about how to populate this table here, which doesn't rely on any special, which doesn't involve any special tricks which are customized for particular states. And so here's an example of such an algorithm, which is a tensor network. A tensor network exactly is, like I said, a map from operators to real numbers. For example, I just computed for you a copy of the Mera network for the ket state and for the bra state here in the bottom. And if you take this Mera network, and if you contract it with some particular operator, which is an input, I put some operators here, and contract all indices, this network will evaluate to the number, and that number will be the expectation value we're looking for. But notice that we are not computing these correlation functions in a haphazard way. We are putting an operator here, and then there is a specific procedure I have to do, which is contract the tensor here, contract the tensor there, contract the tensor there. And the sequence of contractions of tensors is the way in which I arrive at my expectation value. So I specified the state through an algorithm which starts from the operator and returns the number. That algorithm is the contraction of the tensor network. Yes. So I want to think of, I want to take this example and I want to take it very seriously, but on an inspirational level. In other words, I want to imagine that every state is an algorithm of some type, but maybe it's not actually a tensor network. So take all the things I just said about tensor networks and try to generalize them a little more broadly. Instead of committing to a tensor network, let me just imagine that the state is defined by a sum of algorithm for computing its correlation functions. And then there will be some, okay, so now as an algorithm, a tensor network, as an algorithm consists of a sequence of tensor contractions, yes? So if I want to generalize this picture, I have to ask myself, if I imagine that the state is an algorithm, there must be some subroutine in the algorithm which is being repeated over and over, and hopefully. And then in the original motivation for, let's say, the volume proposal for complexity, Lenny and others imagined that the spatial slice of ADS is like a tensor network, and then they said complexity should be volume because that's how many tensors there are in the tensor network. Basically what they're saying is that a single unit of complexity is a tensor contraction. And I want to say, in this more general algorithmic language, that would be like saying that a basic unit of complexity should be a single call to some particular subroutine, which is a bottleneck for this algorithm. But that's counting such calls to a special subroutine is exactly what query complexity is. So what I want to say here is that by discussing query complexity, I'm just being completely faithful to the original motivation for the volume proposal, which goes back to a tensor network, a hypothetical tensor network picture. I'm just being a little more general in that I'm not presuming that the algorithm in question is a tensor network. Maybe it's some more general algorithm. That's the only thing that's different from the original thinking about complexity. Okay, so the proposal that I am putting forward here is that state complexity in the CFT is really a query complexity of the optimal algorithm that sends operators to their expectation values in the particular state. Any questions or comments about that? So if there are none, but please tell me if there are, then let me tell you about how to construct such an algorithm. So in the next couple of minutes, we will construct this algorithm, and then we will ask, okay, now that we have an algorithm, what kind of subroutine is a key subroutine for the execution of this algorithm? We'll identify such a subroutine, and then we'll count them to identify query complexity. And that's what we'll do. Okay, so as a guide towards the general construction of such an algorithm, let's go back to the state which is probably best understood of all states in physics. in field theory, which is the ground state of a two-dimensional conformal field theory. So here it is. And I imagine that it has some bulk representation in terms of an anti-de Sitter space. So I imagine that the CFT is holographic. So here is a picture of the bulk, of an equal time slice of the bulk. Here is the spatial coordinate, and this is the bulk coordinate z. And I imagine that there is some cutoff, which I drew here as a dashed line. And I'm asking, what would I be doing if I wanted to compute correlation functions in this state, but I want to do it in a way which is very careful about this cutoff, first of all. And second of all, I don't want to use tricks about this specific state, like DiFrancesco or others would do in a textbook. I want to do it in a language which is as faithful to the bulk as possible, as in it takes this cutoff surface very seriously. And so here I propose for you a method for computing all vacuum correlation functions in this way. Let me actually start from the vacuum, okay, and translate it. So this is an operator that generates a finite translation, and translate it until the place where I encounter the first operator, O1. Remember, we're taking some inputs and I'm generating outputs. But this translation is not just any translation. I picked it so that it has the bulk interpretation of traveling along the cutoff surface. And so I'm going to take this operator, and then I will continue traveling along the cutoff surface until I encounter another operator. And I'll continue traveling along the cutoff surface, this operator, until I end it, or until the cutoff surface closes. This was global ADS, or a CFT on a circle. Otherwise, I go to minus infinity. And then I take the bra with the of the ground state. So the reason why this is a generalizable way of computing correlation functions is that I didn't need to know any, I didn't really use any tricks about the state to compute the correlation function. The only thing I was doing was sliding along the cutoff surface. I imagined I could do it. And then I picked various operators, and then I slid again and picked various operators, and in the end, I formed a trace of the resulting object, because this expectation value is really a trace. So our philosophy will be, at least it works for the vacuum, is to compute correlation functions by imagine that I have a cutoff in the bulk. I'm going to find an operator that translates me just along the cutoff, and then I will be sliding along the cutoff and collecting input operators, sliding along the cutoff and collecting further input operators, and at the end of the day, I'll just form a trace. And this gives me all correlation functions that I would want. In the case of the ground state, I happen to already know ahead of time what operator is going to do the sliding. It's just L minus 1 times dx. It's dx because it will be finite exponentials of this guy that will give me finite translations. But an infinitesimal translation is L minus 1 dx. Now, in general, I will not know that this kind of operator is L minus 1 dx, but I will know ahead of time as a formal statement that it must be an operator valued 1 form. I must have an operator which performs translations, but it must be a 1 form, because if I take exponentials of integrals of it, such as the path ordered exponential, then I will get some finite transformation. So it must be of a form, some differential form valued in operators. I might as well call this operator DDS, where S parameterizes my cutoff. This is just a shorthand notation for whatever operator does the job of sliding along the cutoff. And in the vacuum case, DS, DDS, an operator valued 1 form is just L minus 1 dx. Okay, so now let's take what we learned from this slide for the vacuum and apply it to some other state. So here it is. And I'm not going to assume in this state that the cutoff surface is horizontal or is uniform. It can have some various features like this bump. But I imagine that I know how to slide along, which is, I know some operator, which I will call A, which performs the sliding job. It's an operator valued 1 form that does this. Well, in this case, An exact repetition of what we had on this slide gives me an object of this type. I start with my overall state, a state without any scale, and then I will translate along the cutoff until I meet some operator, some input. Then I'll translate along the cutoff, and then I'll take another input, and I'll keep going, translating and taking inputs, translating and taking inputs, and at the very end of the day, I will take an inner product with the bra of the corresponding global state. This object, which can be evaluated for any input operators, is what I would call the state at the cutoff. So psi here is the state without the cutoff. It's the state in the fundamental theory. But what I have created for you here is a state at the cutoff, because it only takes inputs at my given scale. In fact, that last statement I haven't really imposed yet, that last condition. So let me tell you how to do it. I want operators which simultaneously commute with the modular Hamiltonian of one little interval which is tangent to the cutoff and the infinitesimally neighboring one. This condition, so it's a statement that we know from various things, mostly from, well, eventually from, or at the bottom from subregion duality, but it was a statement that was made most explicitly by Aitor Lewkowicz and Tom Faulkner, that operators that commute with the modular Hamiltonian, and therefore with the whole density matrix, localize on the RT surface. If I want an operator to be on a cutoff surface, so that it's a good input for my cutoff, it's in the domain of the operators to numbers map. If I want that, then this guy has to commute simultaneously with both this the modular Hamiltonian for this little region and for that little region, both of them being tangent to the cutoff surface. And so I'm assuming that all the operators on which I will evaluate this map will satisfy this condition. They simultaneously compute with rho and rho prime, such that the entanglement wedges representing rho and rho prime are both tangent to my cutoff. So that's a comment about the domain of this map. But if I just forget about the domain, forget about the blue parts in this expression, I want to say that this expression, this guy, is literally the state at the given cutoff. So I've constructed it modulo the fact that I still don't actually know what this A is. I just assumed that I had it. So let me tell you about how to make A. So there will be two steps in it. One is modular parallel transport. I told you that's one of the logical starting points for this presentation. So it turns out that we know a CFT operation which does what these brown arrows would do in the bulk. As in, if I'm mapping one entanglement wedge to another, both of them are relevant to the problem because I assume that they are tangent to my cutoff surface. There are various ways to map them, but one of them is just to rotate around their common point here where the RT surfaces intersect. And if I want to satisfy that condition, that this point gets mapped to itself, then that's called modular parallel transport, and we know exactly how to do it. So I will call the generator of modular parallel transport IDV. I put a D there to emphasize that this is a one form. But it doesn't do the job that A is supposed to do. It only goes part of the way. You see, A is supposed to take the cross and put it to the circled cross here. But instead, it maps this point over here from the bulk point of view. So it's not sliding. It's actually rolling if you think about what it's doing relative to the cutoff surface. But I'm going to construct A as a sequence of that operation and something else. If I just find another operation, which will then take me from here to here, then the overall operation that I will have generated will be just what A is supposed to do. So what I'm saying is that 1 plus A equals 1 plus IDV. That's the generator of modular parallel transport. By the time I've done this, I have mapped things here. But then I assume that there's one more thing I have to do, and let me tell you about this other thing. So what is that other thing? It has to move this point to that point. So how do I find this? Well, it's a motion along the RT surface of the new entanglement wedge, and therefore it must be something that preserves the entanglement wedge altogether. So it must be a zero mode of the modular Hamiltonian. Now it turns out, okay, so that's this condition here. It turns out that there is a that the guy that does this is actually completely determined from DV. I don't have time now to explain to you exactly how to construct this object. In the case of the generator of modular parallel transport, I could just refer you to the previous paper we wrote, which is this paper. This DP here is not yet described in any paper, so you have to take my word for it that we can construct it, but we can. And the statement that I want to convey to you right now is not about how to construct it. I just want to tell you that it is completely determined from DV. And therefore, it is a CFT object. So a key thing that I wanted is I wanted my construction of the state to be purely a CFT construction without any bulk input. DV from the previous slide was entirely defined in the CFT, and I'm saying that DP is an object derived from it, therefore it is also entirely a CFT object. There is a certain technical construction that I won't get into, where we can view DV as the velocity, and then DP is an acceleration in some sense. But unfortunately, I don't have time to talk about it in any more detail. The punchline, though, is that I have some way of constructing this A, and moreover, the A is constructed from things which are entirely well defined in the CFT. So A is not something that I have to look up in the bulk and only then I know what it is. Actually, I know it purely from CFT input. Okay, so let's assume, that I know this A. I just told you a little bit about how to construct it, and let's go back to our state. Okay, in this case, I wrote out what our state is supposed to be, the state at the cutoff, but only left places for two inputs, O1 and O2, input operators for which the state is supposed to map to their expectation values. So I want to say that there is a special feature of this expression that we can use, which is that this A is a combination of modular parallel transport and zero modes. Zero modes commute with the modular Hamiltonian of the instantaneous entanglement wedge, which is associated to some tangent geodesic to my cutoff. Therefore, the part of A, which is a zero mode, doesn't do anything to this entanglement wedge. The other part is modular parallel transport, DV. But that part is exactly defined by the condition that it moves entanglement wedges in a particular way. So it maps one of them to the other. It follows from this that if I happen to have a density matrix for one of these density matrices in the family, which is specified by the condition that their entanglement wedges are tangent to the cutoff, if I had one of them, then conjugating it by a Wilson line of this A will bring me to another such density matrix in the same class. So in particular, if I took one of these rows, conjugated by this kind of Wilson line, then I'll get another such row. For instance, I could move row 1 to row 2 in this fashion. And it follows from these conditions that I just specified. So since I know this, it turns out that I can simplify what I call the state at the cutoff in a very drastic way. So here I wrote the same expression again as on the previous slide, but one of these Wilson lines that are over here, I factorized it here into two pieces. This is a product of a Wilson line from -infinity to S2. And I want to say that this factored product is of a very special form, which allows me to simplify the whole expression in this way, where I don't just have the outer product of my fundamental level state, cutoff-less state, but actually I just have a density matrix for one of these tangent geodesics. So how do I see this? Notice that this expression is an operator that acts on this entanglement wedge. That was my assumption about the inputs for my state. But then it is conjugated by Wilson lines that take this entanglement wedge to this entanglement wedge. So in the end, this thing is really like a row 1 precursor for something that actually acts over here. I say it's a precursor because it's an operator which has the same action that this operator would have had, but it has that action defined for this to act on this entanglement, the Hilbert space of this little region. Now, what about this O1? Well, that's already something that acts in row 1. Now, if I so now I have a situation where this whole trace actually has something that acts on O1, something on row on this little Hilbert space, something else that also acts just here, and then I have this Wilson line. But this Wilson line, I want to say that at this point, everything in this expression, I'm just forming a trace, actually only depends on what happens inside this entanglement wedge. Therefore, I can take this trace, and first take it over the complement of this region. This will produce what I call row 1 here. It will just take the density matrix for just this little region, and then these Wilson lines just guarantee that I could have taken this row 1 and brought it to any arbitrary point, to any other entanglement wedge which is tangent to the cutoff. So this was a long-winded and probably not a very clear explanation, so I apologize for that. But the punchline is that this expression simplifies, and it simplifies to this much simpler expression which only involves Wilson lines of A, and it involves one starting entanglement wedge or one starting density matrix for any one of these regions which are tangent, entanglement wedges are tangent to the cutoff surface. I just have to take one of them, initialize this way, and then translate it using A, Wilson lines of A, take inputs, translate, take inputs, and then I form a trace at the very end of the day after I have scanned through the whole cutoff surface. So this is the state as we have concluded. I have a density matrix for one little region whose entanglement wedge would be tangent to the cutoff surface, and then I will just do a sequence of translations, reading an input, translations and reading an input. These blue dots that I left here are the places where the state is waiting or looking to absorb an input. Once you put an input there, you can meaningfully form a trace and you'll get a number. That number is the expectation value for the operators you have put in. So this really is the state at the cutoff. Notice that the cutoff was very essential for our discussion. It determined this row. It also determined what A is. A was supposed to be scanning along the cutoff. So it's something that I can only define after I know the cutoff. So we have defined in CFT language a state at the cutoff. And notice that we have defined it in the form of an algorithm. Yes. So the state knows about the cutoff. It is entirely in the CFT language, and it is an algorithm like I advertised. So now that we have the state at the cutoff, which is one of the main conclusions of this talk, let's talk about the query complexity of this state. Before we had the state in the form of an algorithm, it didn't really make much sense to talk about the query complexity of the state. But now that I have presented to you in the form of an algorithm, we can talk about the query complexity of it. So let's talk about that. Now, query complexity is supposed to be the number of times that a certain bottleneck subroutine is being called. So it has to be something that is repeatedly used over and over in the state. It's really clear that in this case, the repeatedly used object is just this thing. It's an infinitesimal translation along the cutoff and reading off a new input. The combination of them is the subroutine we're talking about. In fact, to bring it to a language which is a little more familiar to everyone, now that we have written this state in this form, I can present it as a tensor network, which is not any old tensor network, but a matrix product, where I just repeat the repeated tensor in my matrix product state is a tensor that performs this job. And then at the end of the day, I also have to multiply it by rho infinity, which is one particular tensor, and form a trace, which is the reason why I close the loop here in the tensor network picture. And so in some sense, if I want to count these things or compute the query complexity, I am back to the thing that Lenny and others would have wanted to me in the first place, which is to count tensors in a tensor network. But I have to be mindful of what these tensors, or what these objects are actually doing. So here is a little reminder of what this thing does. It maps one entanglement wedge, which is tangent to the cutoff surface, to another entanglement wedge, in such a way that we are entirely sliding along, not doing anything else, but precisely sliding along the cutoff surface, and then it reads one more input over here. Maps an entanglement wedge to the next and reads off an input. So it would be a little unfair to just literally count these tensors, because sometimes sliding along the cutoff surface is easier and sometimes harder depending on the shape of the cutoff surface. So we have to be a little more careful about this. The little more careful thing to do is to ask, well, what properties or what is the principle that should guide us towards quantifying the complexity of this operation? And the principle is this: it should be a measure of how difficult it is to map one entanglement wedge to another. Because remember, that's what A is supposed to do. It's supposed to map one entanglement wedge to another. If I think of the entire spacetime as one big tensor network, then the difficulty of that is related to how big these red regions are, the regions that are highlighted in red here. Namely, if I'm moving this green entanglement wedge to this blue entanglement wedge, there is a little piece of the tensor network that formed this entanglement wedge, which I have to erase, and another piece that I have to add. And the width of these wedges, the width of these slivers, it should be a measure of how hard it is to move one entanglement wedge to another. It turns out that if I want to be faithful to this intuition, there is an essentially unique, technically defined metric in the space of density matrices, which matches this heuristics, which is, in other words, which is consistent with this law of parallel transport. That's what we're really doing. That metric is called the Kirillov constant Suryo metric for the Shekvist connection A, but I'm not going to be talking at this level of technical rigor. So suffice it to say that there is some proposal out there which we can, which mathematicians have developed, which I can just pick and use and apply. And again, I want to stress that this metric is entirely defined in the CFT language. In other words, if I'm going to use it for quantifying complexity, I will not be using any bulk input, all boundary language. However, if there is a bulk, so this is well defined even if the theory is not holographic. But if it is holographic, then by construction, the metric distances with respect to this metric I'm talking about are going to be related to how wide these slivers are over here. And more geometrically, what this is that they will evaluate to just the extrinsic curvature of my cutoff surface itself, weighted by the length element along the cutoff. It's just a fact that this metric will evaluate to this object. So if so, then my query complexity from the bulk point of view, assuming that there is a bulk, again, this is entirely a CFT construction, so there doesn't have to be a bulk for this to make sense. But if there is a bulk, then this object is going to evaluate to this, to the integral of KdS along the cutoff. Now, let me just say that I can declare it success right here. Why? Because this object is always going to be bigger when the region enclosed by the cutoff surface is bigger. So in that sense, it does exactly what complexity on a qualitative level should be doing. It grows when the spatial slices are bigger. It is not in general equal to the volume or the action in the Wheeler-DeWitt patch, but it is something that captures the essence of what it means to be bigger in ADS space. Right? But it's a new thing and a new proposal for bulk site complexity. However, if I use it in pure ADS-free, it turns out that by the Gauss-Bonnet theorem, this object equals to this quantity, so up to the 2 pi and the prefactor, which is the Ricci scalar on an equal time slice of ADS space, it actually is the volume proposal. And so when we talk about states that we understand best, such as the ground state of holographic CFT2, so the bulk dual is pure ADS, then we're actually agreeing with the volume proposal. But in more general states, we do not. We are not agreeing with them, but it's okay. Still, we got some measure of complexity, which truly measures spatial sizes from the bulk point of, from the boundary point of view. And I emphasize that we're doing it entirely in the entirely in the CFT language. So we're not looking up what happens in the bulk and only then modifying our definition of complexity. The complexity we defined here this query complexity is entirely a CFT concept. So therefore, I declare success, and that's all I have to say today. Thank you very much.
Okay.
Thank you.
Any questions? If not, I think we have we are not really, we are running out of time basically. So let's thank Bartek again, and okay.
Thank you very much for your attention.
Yeah, maybe I'm not sure if this is a relevant question. So just this figure, these slides, this purple line circle looks very much like M-partite holographic reflected entropy. If it's maybe not very precise, just basically that object was defined if I have many small RT attached to the boundary, then I have to take the really minimal wedge. But if you extend that kind of cross section into M-partite case or infinite many-partite case, it basically goes to this one.
So I don't have any further comment on this, except to say that this picture looks like some other thing as well, which is the construction of differential entropy.
Okay.
So I can offer a comment about how it's different from differential entropy, but about the n-partite reflected entropy, I haven't thought about this, so I don't know what to say. About differential entropy, though, so remember there was a construction that my collaborators and I came up with for computing lengths of such curves. And it also involved doing something about these tangent geodesics. And basically it was adding additional entropies of one such tangent region conditioned on the intersection of this tangent region and the next one. And so when you do that, you get the length of the curve. And here we are getting the extrinsic curvature of the curve. Now, so typically a curve, if you only care about the neighborhood of the curve, but you don't care what happens globally around it, only has two invariants, which is in 3 dimensions, only has two invariants. No, in 2 dimensions, only has two invariants. Its length and the integral of its extrinsic curvature. When you go to 3 dimensions, there's also torsion. When you go to 4 dimensions, there's a further thing, which basically means which is like a generalization of torsion, but now we're talking about how the plane that contains both the velocity and the tangent and the torsion is rotating itself. And so in an n-dimensional space, a curve will have generally n types of invariants. And what we just did here is we computed this other invariant in a 2-dimensional case, essentially working on an equal time slice of the geometry. So there is some, and it's interesting to compare what length is relative to this guy. But I think that the fact that we got the other invariant for the curve is kind of reminiscent also of Lenny's original motivation for complexity. At some point he wrote a paper, entanglement is not enough. And the complexity paper soon followed. So there was a sense that, okay, now I know how to, what to associate with codimension 2 surfaces, but what about codimension 1 objects or codimension 0 objects? This is similar in the sense that we had differential entropy combined in entanglement entropies in some fashion. That gave me one invariant, but now I should get another invariant out of collecting other things which are not entropies, and that other invariant will be complexity. Not surprisingly, thinking about it this way gives us the second non-trivial invariant of the curve in the particular case of a homogeneous geometry.
I see. So, okay. So basically, I want to, maybe, I'm not sure it's related to the talk, but certainly you are the right person to ask. Let me take the opportunity. So if you consider the kind of flow to the center of the block about these purple curves, a circle. So is there a way to establish some kind of flow equation? Because you can certainly choose the.
Excellent question. Thank you for asking this. So, so I have a, there is a description for what to do in this case. Not a detailed description, but some kind of description in the case where we are in pure ADS free. And that's in the paper that already came out with Chen-Bowen and Wang Ziji. So we define, basically in that paper, we talk about this object, but without trying to be general, and only in ADS-free language. It's a little hard to recognize that it's the same thing, because in there we're using the Chern-Simons formulation of gravity to define it. But if you take the thing we defined there and compare it with this, soon you'll realize that it's actually the same thing. So that paper is reformulated relative to this talk, but the content is the same, only specialized to ADS. And in there we make comments about what it means to go from a larger region to a smaller region. But these are not detailed comments. So anyway, for now, let me just send you to that paper for comments, but then we can discuss in more detail in the coming days. I'll be happy to talk about it.
Okay. Sorry, the paper by whom?
Oh, by myself and my last paper on the archives. It's with Bowen and Wang Ziji.
I'm certainly looking at it. Okay, thank you.
Okay. Any other questions?
Yeah. So this method can be applied to evaluate the complexity for a concrete CFT model that is not holographic, right?
Yes.
So you can, I mean, you can do explicit calculation and to get, for example, the asymptotic behavior for a general model, right? Oh,
you're asking how this scales for general models?
Yeah, and I mean, it seems that you say that this is a kind of definition. I mean, if you can do an explicit calculation for this quantity.
Yeah. So the comment here is that, so I don't know how it scales in general, and that's not an easy question. And just to give you, but let me give you a sense of what controls it. So, at the end of the day, I said query complexity is going to be some distance, which is compatible with this object A that I constructed. A can be defined in general, but the condition that A gives a sort of controllable geometric thing is coming from here. It's the statement that A is the relevant part of A for the purpose of computing these distances is generated by this dV, which is modular parallel transport. And modular parallel transport corresponds to just a rotation about the common intersection point. This rotation here is, well, so modular parallel transport in general, in holographic theories, is going to be generated by the modular scrambling modes that featured very prominently in Lampros's talk earlier this morning. Yeah. And in that case, we can confidently say that this distance relative to this metric, which will be query complexity, is basically the angle by which I'm rotating here. That's how extrinsic curvature shows up. But in non-holographic theories, modular parallel transport will be will involve many operators which are not scrambling mode. And when they're not scrambling modes, we don't have this geometric picture. So, the holographic conclusion that query complexity is like extrinsic curvature of the cutoff surface will get jumbled up by the fact that generators of parallel transport will no longer be scrambling modes, but a bigger mess. And so I don't have any control over distances in that metric in non-holographic settings, because when they're not scrambling modes, it's really hard to say what the distances are, at least for me at present.
I see. Thank you.
Okay, so I think we are on a tight schedule, so I think it's time to let's thank Bartek again, and Lily, are you online?
Yes. Let me share my screen. Okay.
Thank you, Bartek.
Thank you.
Thank you.
Okay, can you see my screen?
Yeah, I can see you.
Yeah.
Okay, that's wonderful.
Okay, so our second speaker is Lily from ITP, and he will be telling us about magnetotransport, hydrodynamics, and holography. Okay, let's welcome.
Okay.
You have the floor.
Okay, thanks for introduction. I would first thank the organizer for inviting me to give a talk in this nice workshop. So today, my talk, this is the title, and my talk is based on these two recent papers with my collaborator, Mathieu. She is now moving to Lee Institute as a faculty member, and I saw he's here in this Zoom. And Sebastian, he got a PhD in Jena University and now moved to IFT as a postdoc. And Yu Sen An and Teng Ji are two PhD students in ITP CAS. Okay, as we know, the holographic duality provides a framework to deal with strongly coupled systems. Actually, remarkable progress has been made in applying this correspondence to nuclear physics, condensed matter, quantum information, and so on. So in today's talk, I will mainly focus on this application, I mean quantum matter in condensed matter systems. So there are many challenges for strongly coupled quantum phases of matter. So for example, the breakdown of Fermi liquid description. So we are dealing with quantum matter without quasi-particles. So there are also a very complicated phase diagram with different orders. So a typical example is the phase diagram for high TC cuprates. So here we have antiferromagnetic order, we have some charge density waves, superconductivity, and also stranded metal phase. And there are also segmented Fermi surfaces like Fermi arcs, anomalous transport, Planckian dissipation, long random entanglement. So here our strategy is to study solvable models that might be in the same universality class as the strongly coupled systems we are interested in. So our goal is to have some useful lessons or universal features shed light on the basic mechanism underlying the dynamics. So we suggest that we are considering solvable models. So it often implies working with some bottom-up toy models. So the model might be very simple, but we hope this model can capture the main features of the system we are interested in. So actually, we have some useful guiding principles, including symmetry, causality, instability, and so on. So I will talk about these guiding principles later. Okay, this is the outline. So I will mainly focus on the first part, I mean the magnetophonons and Goldstone modes. If I have time, I will also talk about the magnetotransport and the metal insulator transition. The last one is the summary and the discussion. Okay, let's go to the first part. And we will talk about the magnetophonons and type B Goldstones from hydrodynamics and holographic duality. So as we know, symmetry and symmetry breaking play fundamental role in our nature, and in particular in theoretical physics and condensed matter. So a very nice example is the Girdlestone theorem. So it tells us that the breaking of any internal continuous global symmetry guarantees the existence of gapless modes. And the number of this mode is equal to the number of broken symmetry generators. And furthermore, the dispersion relation is linear. We mean the frequency and the wave number has this linear relationship. And the number of Girdlestone modes is given by the dimension of the coset space. I mean G over H. Here, capital G is the broken group, and H is the preserved small group. So actually, the number of Girdlestone modes, I mean NGB, is given by this relation. It's counting of the flat directions of fluctuations of the order parameters. So actually, to have this very nice and strong result, we have some additional requirements. So we consider Poincare invariance, and we consider eternal continuous global symmetries, and for non-dissipative systems. But actually, there are many systems in our nature which do not satisfy these requirements. And this will lead to very interesting phenomena. So for example, so the number of Girdlestone modes is less than that of the broken generators. And the dispersion relation of the Girdlestone modes is nonlinear. And the last one, the Girdlestone modes are not propagating, but diffusive. So let's explain this interesting result one by one. Okay, for the first case, the reduced number of Girdlestones is mainly due to the fact that the broken generators, say Q alpha and Q beta, they commute with the Hamiltonian, but not with one another. So here we see this Q alpha and Q beta. They commute with the Hamiltonian, but they do not commute with each other. So the symmetries are not independent. The very nice example is to consider simultaneously breaking space-time rotations and translations. So from Poincare algebra, we know the angular momentum J and the momenta P have these commutators. So it's non-vanishing. So these have very interesting consequences. This explains why we do not observe any Girdlestone mode for rotations in a crystal. Okay, the second case, we mean the Girdlestone bosons have a dispersion relation that is nonlinear. For example, we mean the relationship between the frequency and the wave number have this nonlinear power. I mean, n is not equals to 1. So which is typical of non-relativistic systems. Actually, the fundamental point in this discussion is that the effective low energy description can be given by this one. So here, pi is the Girdlestone fluctuations, and rho AB is an antisymmetric matrix. It's given by the commutator of the broken generators, QA and QB. This is called Watanabe-Browner matrix. Actually, depending on this power, we have two different Girdlestone modes. In the first case, we call type A, the power is an odd number, it's 2n minus 1. In contrast, in the so-called type B mode, the power is even. Actually, the rank of this rho AB can determine the number of the different types of the Girdlestone bosons. Here, from this paper, we show, so the number of B mode is given by the rank divided by 2, and the number for the type A mode is given by NGB we defined before, minus the rank of this matrix. So the total number is given by NGB minus rho AB divided by 2. So a typical example for this case is to consider ferromagnet. So it spontaneously breaks SO3 to SO2. So naively speaking, we will have two standard linear Girdlestones, but actually there is only one Girdlestone mode, the magnon, and which is quadratic. We mean we have this kind of Goldstone mode with n equals 1. Okay, the last case is for the diffusive Goldstones. Typically in dissipative systems, these diffusive Goldstone modes can appear. For example, these quadratic modes have been observed in several physical systems, for example, in this paper, as well as in holographic models. Actually, more exotic modes like this K24 can arise within the Hydra theory of fractals. So a very interesting example here is to consider a flock of birds. So here, this picture, it gives the dispersion relation with the diffusive mode. Actually, in this talk, we will study the dynamics of magnetophonons. So magnetophonon is the Goldstone bosons which appear in systems with spontaneously broken translation symmetry, but at a finite magnetic field. So why we consider this? The motivation is as follows. So on the one hand, these modes are very interesting because they are another example of type B Goldstone modes with this quadratic dispersion relation. And we will show actually the two linearly propagating mode without a magnetic field. We mean the longitudinal and the transverse phonons. For the phonon have this linear relationship, and the speed is given by the V parallel and the transverse. They will combine together to a single quadratic mode, the magnetophonon. On the other hand, from a condensed matter perspective, the physics of this magnetophonon is very appealing if we even consider the small explicit breaking of translations like impurities or disorders. Actually, the dynamics of this magnetophonon peak with respect to the magnetic field can reveal the fundamental nature of the disorder responsible for its pinning mechanism. So let's first consider some fundamental aspects of magnetophonons. Actually, at a finite magnetic field, the commutator for the momenta is given by this relation. Here, B is the magnetic field, Q is the electric charge. So at the level of the effective action of the Goldstone fluctuations associated with the momenta, so the presence of magnetic field gives the new term to the effective action. So here, so according to our introduction before, the Webner-Brauner matrix ρIB is given by this Xij. It's non-trivial. So in 2 dimensions, its rank equals to 2. So using the formula, the counting rule we just introduced, so we have Na equals 0 and Nb equals 1. This is nothing but the magnetophonon. So actually, these 2 linear propagating sound mode. So here I mean this linear Goldstone mode, the transverse and the longitudinal phonons, and they combine together to a type B mode, this magnetophonon. And furthermore, it also has a partner, a gapped mode we call the magnetoplasma. So how does it happen? So we can understand this from the Hydra description. Actually, at a finite magnetic field, the transverse and the longitudinal phonon, they couple together and resulting in the frequency like this. Here, omega plus and omega minus, we have 2 modes. Here, omega C is the cyclotron frequency, is proportional to magnetic field. And omega parallel and the transverse are the frequencies of the longitudinal and the transverse phonons. With this dispersion relation, this position moment with these 2 modes, the mass, the omegas has quadratic dispersion. The mass load B magneton and the load C at the momentum has non-zero set cyclotron frequency, so it's gapped. This gapped mode we call the magnetoplasma. Actually, if we further introduce some small explicit breaking, like disorder, impurity, the dispersion relation of the magnetophonon will get modified to this relation. Here, omega c, here is the, as we mentioned, is the cyclotron frequency, and omega naught is the pinning frequency due to the impurity or disorder. Actually, you see at a zero momentum, I mean, omega minus is equal to omega peak is not zero. So this mode has a finite gap. Actually, the dependence of this gap with respect to magnetic field is very easy to measure precisely in experimental side, and it can give very important information of the types of the disorder in the material. So actually, from the classical hydrodynamics, it gives this kind of behavior. We mean the peak is proportional to 1 over magnetic field. That means from the classical hydro, this peak will decrease and will increase the magnetic field. However, this is not the case in many materials. Here we show some real data from some two-dimensional materials. You see in this case, the peak increases with the magnetic field. That means we need to go beyond the classical treatment. Indeed, the classical hydro description is only valid when the magnetic length LB is much smaller than the disorder correlation length Kc in this classical regime, so we can trust the hydro description. So in the opposite limit, we say the LB is much larger than Kc. We are in the quantum regime. So they can have behaviors very different from the classical hydros. Actually, a good example is for the dilute disorder by considering specific corrections. For example, in this paper, they give this kind of dispersion relation. It's the peak as a function of magnetic field, sorry. And this power gamma is between 0 and 1. It's very different from the classical hydro. So now with this in hand, we go to the holographic model. So this is called the holographic axion model. So here R is the Ricci scalar, and this is the U1 gauge field, and X is this kinetic term for the massless scalar we call the axion, because it has this particular configuration, so it's proportional to the spatial directions. So here kappa is a constant we call the disorder or momentum dissipation. So thanks to this setup, we are able to give the analytic solution for these black holes. So here U is the holographic radial direction, mu is the chemical potential, rho is the charge density. Here capital B is the magnetic field. Here for the Blakeney function, here UH is the event horizon. So this solution is for general this potential V as a function of X. And from these black hole solutions, we can have the temperature given by this quantity. So actually a very interesting feature is that this very simple model can give different types of breaking translation invariance. So a typical example in the literature is the polynomial potential. We mean we have this linear term and this nonlinear term. Actually, this term is for the explicit breaking of translation invariance. And this term is for the spontaneously breaking of translational invariance. And there is also a very interesting case we call the pseudo-spontaneous breaking. So where the breaking is mostly spontaneously. So in this regime, we mean the alpha is much smaller than 1 and the beta is much larger than alpha. Actually, there are many papers to consider this kind of models. So in the literature, actually the main idea why we have different breaking translations is because depending on the power, so this term can be a source or wave. depending on the power. So when this power is smaller than 5 divided by 2, this is the leading source term. With higher power, this is not the leading source term, it's a wave term. So in this case, we have different way to realize the translation symmetry breaking. So as a warm-up, so we first consider the hydrodynamics. So here we first investigate the hydrodynamic description of this holographic model with spontaneously broken translations at a finite charge density. So here we turn off the magnetic field. Actually, previous hydrodynamic description was lacking fundamental terms to match the holographic result. Actually, this year, in this paper, the authors provided an improved hydrodynamic description. They introduced the crystal pressure. So in the first part, we just want to check if this improved hydrodynamic description can match the holographic result from this model without a magnetic field. So here, this is the main result from the hydrodynamics. So I mean in 2 spatial dimensions. Actually, in the transverse sector, there is a sound mode, meaning this velocity, this is the attenuation constant. And in the longitudinal sector, we have 1 sound mode and 2 diffusive mode given by this diffusive constant. Actually, this quantity, the velocity and the diffusion constant, can be given totally fixed by these thermodynamical quantities. So there are many, this seems very complicated. So let's skip all details. I just stress some main point. So here the diffusion constant D can be solved by solving these algebra equations. And here P is omega is the free energy. So the pressure is given by minus free energy from the from thermodynamics. So here the key point is this quantity. This P we call the crystal pressure. Is the difference between the thermodynamic pressure, the P, and the XX component of the stress tensor. And for this quantity, they can also define the entropy, the charge associated with this pressure. So actually, to sum up, this is just the main result of the hydro. So, but all these quantities can be calculated using the holographic model. So here we show our result. Actually, here different curves. They are from this hydro prediction, and these marks are from our holographic result. Actually, in holographic side, so what happens? So okay, so for example, this velocity can be calculated from the Quaternion mode. So we can fit in the Quaternion mode to have all these quantities. So, and you can see they have very perfect agreement between the hydrodynamic framework and the holographic result. You see the different curve and the marks agree with each other. Okay, so now we add a finite magnetic field to this setup and continue to consider the case in which the translation are spontaneously. So we extended this work to consider magnetic field. Actually, at a finite magnetic field, as we introduced before, we expect the presence of a type B mode. This mode and a gapped partner. We have this magnetoplasma and magnetophonon. Actually, from hydrodynamics and effective field theory, we have this kind of relations. This gap is from the magnetic field, is the cyclotron frequency. And okay, so, and the magnetoplasma mode, we call omega plus. They had a damping term given by this gamma B. And the gamma B is fixed by magnetic field and the momentum susceptibility. And this is only valid in small magnetic field. We mean the magnetic field is much smaller than the temperature. So we should point out that a complete hydro theory in the presence of lattice pressure, spontaneously broken translations, finite charge density, and magnetic field has not been built yet. So in some sense, our holographic result will give some first result for this kind of situation. Actually, here we show the result from the holographic model. So we consider this case. So with this power, so the translation symmetry is broken purely spontaneously. So here, the two red lines show the two linear sound mode at a zero magnetic field. You see, there is no gap. And okay, as usual, as we turn on the magnetic field, these two modes will combine together to form the gapped magnetophonons. These star points, this curve. So we have finite gap here, and a quadratic, this magnetophonons. This is this quadratic behavior and the function of wave number. Actually, you see the gap of the magnetophonon, here this gap increases with the magnetic field. And the coefficient of this chi-square scaling of the magnetophonon, so the coefficient decreases with the magnetic field. Actually, the dispersion relation of this type B Goldstone mode at a small momentum have this type. Okay, this quadratic behavior for the real part, you mean this curve, and also for the imaginary part, you see also have this quadratic behavior. Actually, we have this diffusive damping term for the type B Goldstone mode. This is not expected from effective field theory method. Actually, effective field theory gives a K2 force imaginary part. We mean the imaginary part is much smaller than the real part. This means we have the well quasi-particle description. Actually, from our holographic result, we don't have this quasi-particle excitation. This is consistent with the holographic picture because we are considering strongly coupled quantum matter without the quasi-particle description. This is indeed the case. Okay, now we have numerically confirmed the Hydra formula we just introduced. This is a modulus, or these two coefficients given by this velocity and the cyclotron frequency, also given by this relation. And here we show, we compare our numerical result from holographic model to this Hydra prediction. So, and you see, so here is dashed line is from this Hydra description, and the dotted points are from our numerical solution. You see, so when the magnetic field and the parameters is much smaller than the temperature, I mean the energy scale, so this can be the two of each match with each other quite well. So, but at a larger magnetic field, you see they have different behaviors. They have the difference. But so far we don't have a consistent Hydra description to these regimes. So we can just show some result here. But the main point is that at least at a small magnetic field and a small moment, this graviton mass, these two match with each other.
Sorry, but if I
sorry.
Can I ask a question?
Yeah, sure.
So from the model itself, what is the reason? Can we say the reason why this deviation happens? Because I saw a large deviation.
From the model, it's not easy to see why we have this.
I mean, yeah, I mean, what is the reason for this duration?
The duration because the solid curve is from the Hydra description here. And this Hydra description is only valid at a small magnetic field. So I mean, so far we don't have a consistent Hydra description. So this kind of description from Hydra is only valid at a small magnetic field. But the holographic theory, we can calculate any quantity at a large magnetic field. So it's natural to have different behavior at a large magnetic field because the hydro, so far the hydro breaks down. I mean, at least the present framework cannot have any prediction.
I see, thank you.
Mm-hmm. Okay. So if in the future we have a consistent description, I mean, for this case, in presence of lattice pressure or broken translation and magnetic field, we can compare our holographic result to this new framework. They should match. Just as I introduced for this case. So this case is they have the new improved hydro description for the case without magnetic field. You see, these results match with each other very perfectly in this case. But for the case with magnetic field, there are no consistent framework, hydro framework. So here we give a first example. So if if there is a new framework, they should match. So our result should give an example to check the new hydro framework. Okay, here, let's now add a small external source to break the translation symmetry explicitly, like to mimic a disorder or the or impurities. So as we introduced, we need to consider the pseudo-spontaneous regime. We consider this kind of potentials, which mean alpha is much smaller than 1 and beta is much larger than alpha. So actually the optical conductivity can be obtained from the Kuber formula, and this is very easy to calculate using holographic technicals. Actually for the DC value, I mean the conductivity at 0 frequency, we have a very nice formula to calculate the DC conductivity using the horizon data. So this is the general result for arbitrary potential V. This is the magnetic field, this is charge density, and all these values are evaluated at the horizon. So here we give some examples. So here the curves are from these formulas, and the dots are from the optical conductivity. We choose a very small frequency. You see they match with each other quite well. So here we show the evolution of this pseudo-magnetophonon peak and the function of magnetic field. Here we turn on the magnetic field from the smaller to the larger value, from blue to red. This blue value is for very small magnetic field. This red curve is for larger magnetic field. Here you see the position of the peak here. So just increases monotonically with the magnetic field. But at the same time, the width of the peak, which determines the lifetime of the associated resonance, it first becomes sharper and then starts increasing again at a very large magnetic field. So here we also show the image. Okay, this is for the Hall conductivity. This is for the longitudinal conductivity. They have similar feature. So actually we can understand this feature from the quantum modes at the finite charge density and the magnetic field. Here we show the lowest quantum modes. So this we move in the magnetic field. You see have this behavior. Actually for you see the real part just increases and we increase the magnetic field. And for the imaginary part, we have the non-monotonic behavior. So the imaginary part of the quantum mode first decreases and then increases. So the real part of the quantum mode we just show is increased monotonically with the strength of the magnetic field. So this is consistent with this real part behavior. We mean the peak increases monotonically with the magnetic field. And here you see the imaginary part is non-monotonic. This means the lifetime of the quantum modes will first become longer because it decreases as a function of magnetic field, and then decreases at a large value of magnetic field. So actually the motion of the quantum mode is consistent with what already found in this optical conductivity. They are consistent with each other because this peak is controlled by the quantum mode. So more precisely, the numerical value for the peak from the part of the longitudinal conductivity, I mean G sigma XX, and the real part of the lowest quantum mode do not match. This is reasonable because they are different quantities. But at the larger magnetic field, these two almost coincide. Here, the red curve is from the peak of the real part of the conductivity, and the blue dot is from the quantum mode. You see they match at the larger magnetic field. That's why we can understand the behavior of the peak as a function of magnetic field from the quantum mode. Actually, the position of the peak, it seems to be a constant for large value of the fielding fraction is rho divided by magnetic field. Actually, quantitatively, this result in agreement with the experimental fit observed in this paper. Actually, we find a very interesting, robust scaling at a large magnetic field. Actually, we find the peak is proportional to the square root of magnetic field. Actually, this is, here we show the result. You see here, we have this power. Actually, this is incompatible with the idea that at the large magnetic field, the magnetophonon will become light, we mean will decrease with the magnetic field. Even the presence of strong explicit breaking. Actually, our result in agreement with a certain experimental result. You see, so here is the real experimental observation. Actually, it also have this scaling at a large magnetic field. This from this kind of material from this paper. So our result suggests a precisely interpretation of the nature of the disorder. So given by these homogeneous holographic models. Okay, how much time do I have? Oh. Okay,
maybe
so
20 minutes, something. I mean, 15.
Okay, maybe I should speed up. So some remarks. So we discussed this hydro description. And in the holographic model with spontaneous breaking of translations at a finite charge density and a zero magnetic field. Actually, we give the dispersion relation of the magnetophonons in the presence of pinning, and particularly we focus on their type B nature, and we studied the electric conductivity and the dynamics of the pin, the magnetophonons, in the presence of small source of breaking of translations. Actually, our study has revealed the presence of interesting features, both from a theoretical and a phenomenological point of view. So since my time is limited, so maybe I can just briefly introduce the second part. We consider the magnetotransport and the metal insular transition. So actually, the mechanism of metal insular transition is one of the oldest, but still one of the fundamentally least understood problem in condensed matter physics. So it's easy to imagine because a good metal and a good insulator are very different physical systems and can be characterized by different elementary excitations. Indeed, many theories have been proposed to understand this kind of metal insular transition, but the mechanism towards this transition remains controversial and somewhat incomplete. Actually, in the spirit of the effective field theory, a minimal holographic model of disorder-driven metal insular transition was proposed by these kind of papers, but there are still some issues that has not been understood. Okay, here we will understand this theory further and uncovering some generic features. So actually we consider a very similar model. The key point is that we introduce a new coupling capital Y between the translation symmetry breaking sector X and the U1 gate sector. Actually, since we are considering effective theory, there are some consistency which gives some constraints on the couplings. So here, actually, the Y prime is negative plays a very important role in triggering a metal insulator transition. Similarly, in this complicated case, we can also able to find analytic solutions with magnetic field and charge density and momentum dissipation. Okay, this is the formula for the DC conductivity and the resistivity using the horizon data. Actually, let's first consider clean limit. We mean the momentum dissipation is go to 0. So we can, in general, parameterize the coupling Y and V using the Taylor expansion. So actually at the zeroth order, I mean alpha is 0, we have this very nice result. This is expected from the Lorentz symmetry at the finite charge density and the magnetic field. So this is a consistent check of our result. So let's consider the leading correction. So we find the conductivity given by this quantity because we need the conductivity cannot be negative. So this gives the constraint here. And we also, the temperature should be positive. This gives these constraints. To combine these together, we have these non-trivial constraints. So for general magnetic field and charge density, this gives the very strong constraints on this theory parameter K, which must smaller than 1/6. So here we just give a generic constraints on the theory parameter without going to the nonlinear detail of the coupling function. So here we now talk about the metal insulator transition. So for the metallic phase, we mean the resistivity divided by the temperature is positive. In contrast, in the insulating phase, we have the negative sign. So let's first, to simplify this story, we consider high T limit. So we have the resistivity given by this expression. So here we can define a critical charge density rho C given by the shaded quantity, the square root. So you see, as for the small charge density smaller than rho C, the resistivity decreases with temperature is increased given the insulating behavior. And when rho is much larger than rho C, I mean Rxx increases with temperature. So given a metallic behavior. So in this way, we have a metal insulator transition by changing the charge density rho. Actually, from this quantity, we can also find that this metal insulator transition can also be triggered by increasing the magnetic field and also the disorder strength alpha. Actually, the resistivity can scale with a single parameter. So given by T0, T0 is given by this quantity near the transition point. That means different curves for each charge density can be made to overlap by the scaling parameter T0 along the temperature axis. So this gives a collapse of the data onto two curves. One is the insulating branch and the metallic branch. Actually, near the transition point, we have the scaling behavior with the power 1/2. Actually, from this relation, we can find a metallic and the insulating phase are mirror symmetry, which means have this precisely relation near the transition point. This suggests the mechanism responsible for the transport in insulating and the metallic phase are related. So actually, we check the collapse of data to over a large range of parameters. So for example, we consider this kind of model. This is the curve for different charge density, but at a 0 magnetic field. So the different curve corresponds to different charge density. And indeed, we find that different curves can be made to overlap along this temperature axis with the scaling parameter T0. Have this expected scaling behavior. And this is the case. Here we turn on magnetic field by fix the Landau level fading factor. We consider 3/2. Here is a different curve for different magnetic field. We can also have the collapsed behavior. And this is the case. We fix charge density and the magnetic field, but we choose the disorder strength, different alpha. Here you see The different color corresponds to different momentum dissipation. And by scaling the temperature with this scaling parameter T0, different curves can also be collapsed to two different branches, for the insulating branch and the metallic branch. So actually, we see the metal insulator transition can be induced by charge density, magnetic field, and the disorder in our holographic theory. Actually, the collapse of resistivity data into two different curves is held for a wide range of temperatures. Actually, our holographic result agree quantitatively with the experimental observation in many two-dimensional samples and materials. So for example, in this kind of papers, here is an example, this resistivity and the function of temperature for different charge densities, and indeed they can collapse to two different branches. Here we show the phase diagram for our model in terms of temperature and momentum dissipation. Actually, in this model, we have 4 different phases. We have good metal, incoherent metal, bad insulator, and good insulator in different regimes. Actually, so all phases here share the same symmetries of the underlying symmetry, because here we're considering the same kind of black hole solutions has the same symmetry, symmetry breaking, phase transition. So, and thus beyond a simple Ginzburg-Landau description of the phase diagram. Actually, so a next question is there any other probe that is able to characterize different phases here? So we tried many different quantities. We consider specific heat, the charge susceptibility, and even the complexity of formation using the CV duality. So you see these quantities, these local quantity and the non-local quantities share very similar features, but they are all different from this phase diagram here. So far, no good probes have been found. So it's still an open question to find a good probe to this kind of phase diagram. So to conclusion, maybe, okay. So I just introduced. So we showed the mean field linear X model have very interesting results, which are relevant to experimental observations. Actually, the dispersion relation of the hydromoles is discussed, and the magnetophonons and its gapped partner, the magnetoplasma, are identified. Actually, we find the Pini frequency of the magnetoresonance peak increases with the magnetic field in agreement with experimental data, and it reveals the quantum nature of the holographic Pini mechanism. We also showed the holographic metal insulator transition induced by charge density, magnetic field, and disorder. And we gave some universal scaling behaviors, which also agrees quantitatively with the experimental observation in some two-dimensional samples and materials. So actually, the holographics gave a very useful theoretical laboratory, and we stress that our theory is a strong sense of non-Fermi liquid. So there are, in principle, no quasi-particles. We are considering strongly interacting soup with symmetry breaking, and they are possibly relevant for unconventional quantum matter. Okay, there are also many interesting questions. So for example, to consider more complicated systems which break translations without the homogeneity of the background. And so far we limited to ourselves to electrical conductivity. So it's also interesting to consider the thermal response, like the thermal Hall conductivity and the mechanical response. And so there are a lot of work on this kind of model and the generalizations, but the physical nature of the theory, the dual theory, is still not well understood. So to what extent this simple model can be trusted? So which feature they capture different from the inhomogeneous setup, and which phase of matter they are actually describing? So they are interesting questions, and we hope to understand in the future. Okay, this is my talk. Thank you.
Okay, thank you, Lili. So it's discussion time. Any questions? I was just told we have 15 minutes discussion. So
okay. Yeah, we can discuss. Matteo is also here. She can also help to answer any questions you asked. Yeah. Mm-hmm.
So you basically show a lot of different figures by looking
Mm-hmm.
into different physical quantities. For instance, the conductivity, you show this one in this slide. For others, you show that one. Then the question is, which one I should trust? I mean, is this really a phase diagram? Because different.
You mean the phase diagram?
Observable.
Okay.
Yeah. Yes, the last one.
Actually, the phase diagram depends on, you see the parameters depend on, I mean the disorder, the strength of disorder. So if you choose a different disorder, they will be in different phases.
Next slide, I think.
Next slide. This one?
Yeah, this one. Because different quantity gives you different boundaries, right? If I understand correctly.
Sorry. This boundary is from this phase diagram. We just compare if this specific heat can give same feature. So this boundary is just this one.
Yeah, I understand that, because if I forgot about this black one, I'll just look at the heat honest color. It's blue, specific heat, for instance. Let's look at the blue, green, and red one. Okay. Then there's likely other ages, right?
You
can
mean
also
this age?
Yeah, something like that. So the question is, which one is which one is the flag which I can see? Okay, this gives me a phase diagram, because different quantity gives different boundaries.
Yeah, that's true. Different quantity have different boundaries. So the point here, we want to find a quantity that has very similar boundary as this phase diagram in terms of the conductivity. That's our goal. So we don't need to distinguish different boundary. We just have the quantity which have a similar feature as this phase diagram.
Yeah, then the question is, why conductivity is the most robust, which really can give you a correct phase diagram, not the charges stability.
No, maybe actually there are different phase diagrams. This gives the value of the specific heat for different colors. This is for the value for the conductivity. So there are different quantities. So it's natural to give different patterns. Correct?
That's right. But then the question is how to coherently, make a phase diagram and explain all the quantities in that phase diagram. Maybe that's the correct.
No, that's an open question. We don't know. we want to answer. We want to understand.
Any other questions? Comments? Okay. So if not, we are proceeding to the break time. And thank for all the two speakers for this session. And and we are going to end this session now.
Postdoc, all good people. So yeah, wish I could be there in person, but now we're gonna do it virtually. Are my slides not changing? Something wrong here with the sharing. Sorry. Let's try this again. Okay, that works better. Okay, so I will talk about line operators. So all gauge theories have Wilson loops, and they are very important observables. They can tell you about confinement and so on. In 4 dimensions, there are also 't Hooft loops, which are disorder operators as opposed to Wilson loops. And the closest thing we have in 3D to them are vortex loops. They're also disorder operators. But I'm not actually going to talk about them. When we discuss Wilson loop, normally what you discuss are how it depends on the shape and the representation of the Wilson loop, all kinds of information like that. In this talk, I will also not discuss these questions, so the shape will always be the same. So I will look at classification of line operators, but I will not play with the usual parameters that usually people play with line operators, so it will be slightly different. Now, what may be familiar for people is in n equals 4 super Yang-Mills, there is the Maldacena-Wilson loop, which includes a coupling to the scalar, and then there is the regular Wilson loop, which is not supersymmetric. So the Maldacena-Wilson loop is supersymmetric as BPS if it is a straight line or a circle. You can also discuss something called locally BPS, but it's not really important for us. There are also interesting BPS loop operators with complicated shapes if you adjust the scalar couplings. But again, mostly I will not talk about it. Towards the end, I may mention them a little bit. So this was generally about line operators. If we look in a 3-dimensional supersymmetric Chern-Simons matter theories, then they have a rich spectrum of BPS operators that we are still trying to understand. And so I will focus on the case where the loops are all of the shape of a circle. I'm not going to change that. And what they differ by is the couplings that appear in them. So we include, in addition to the usual gauge field that you have to have in a Wilson loop, we change the coupling to the matter fields. In this talk, I will present a new view on these line operators in 3D, a different way of looking at them and classifying them. And I will also present a few new examples. We, of course, should start every talk by a motivation, so you know why I wanted to do this and why you should pay attention to what I'm saying, but this slide is empty. And the reason for that was that actually I approached this project rather demotivated. So these Wilson loops in 3 dimensions were uncovered in a series of papers, and the construction became very complicated. And every paper there was more and more details and big Ansätze with large matrices and many parameters that had to satisfy all kinds of conditions. So you construct these operators, and then you set these conditions. You try that they be supersymmetric, and then you find that some of the parameters that you put into your ansatz have relations between them. Some remain free, and you have several discrete choices that you can make. And in all those papers, they were correct. They had correct classifications, but they left them in terms of a set of equations whose set of solutions would be the answer to the question. But it was all based on this ansatz. So I found this very messy, and I actually didn't want to play with these enormous matrices and all these complicated relations. I have a lot of admiration to the people who figured it out. But so I didn't want to do this. I was working on other things, but then somehow I got remotivated to look at it. And the remotivation came actually from a hint of the solution. So what I realized was that I can map this problem of classification to a famous problem in mathematics of quiver varieties, or Nakajima varieties. And this is what I will describe in this talk. So as a motivation, if you're a Wilson loop aficionado, you should take your motivation that you're going to be studying about Wilson loops. That is fine. But if you're not a Wilson loop aficionado, and I assume that most people here are not Wilson loop aficionados, then your motivation should be that there is a very nice story of theoretical physics here, or mathematical physics, where we find a relation between two different problems that nobody knew that they are related, and we actually find that they are closely connected. So what is the problem? As I said, it's quiver varieties. And what we get is we start with a gauge theory, which is described by a quiver diagram. We take this quiver diagram and modify it in some way to get a quiver describing the line operators. This choice of quiver is actually what was the discrete set of choices in the previous constructions. And then the quiver varieties are algebraic, they are some manifolds, and the continuous parameters live on these manifolds. Now, as I said, part of the motivation is that we are just going to have this nice relation between two seemingly unrelated branches. But from this description, I also uncovered a few more examples that were not noticed before, just some extra relaxations of the conditions in the previous Ansätze that I found via this route. So I gave you the introduction. I will now describe the theories that I want to study. And then I will describe the type of Wilson loops, those that involve just the vector multiplets and those that cover couple to chiral fields. I'll try to be as explicit as possible, but not really overload you with technical details. And then I will explain what is the solution to the problem, what are the moduli spaces, and how is this related to quiver varieties. And I will explain briefly what quiver varieties are. If I have time, I will talk about theories with n=4 supersymmetry, which is in my upcoming paper. So we are talking about 3D n=2 theories. In practice, usually I will assume n greater or equal to 3 when the dimensions of the fields are protected by supersymmetry, but there is a generalization also to the case of fields of non-canonical dimension. And I describe them by quiver diagrams. I will place the theory on the 3-sphere, which is the nice setting for localization, and actually everything with localization works very smoothly, but I will not. This was already done in the old papers of Kapustin, Willett, and Yakov, and it can immediately implement it there. I have nothing new to say, it just works very smoothly. There is a generalization to the squashed sphere, which I will not describe, everything goes through. In the quiver diagrams, I will use the standard notations where the vector multiplets are circles. Now, those not familiar with 3D n equals 2, that is essentially the same amount of supersymmetry as 4D n equals 1. So we have the vector multiplets, we have flavor groups, which are squares, and we have the chiral fields that are arrows. Now, a chiral field also always comes with the anti-chiral component of it that you need in order to write a Lagrangian. Usually it's not written on a quiver diagram, but sometimes I will find it useful. I will need to include them explicitly, and I will write them with a dashed arrow in the opposite direction because they are in the opposite representation of the gauge group. I do not write down the actions for my theories. They're not important for what I'm saying, but you should assume that there is a Chern-Simons term for every vector multiplet. So here are some examples of theories that I will study. So the simplest case is one vector multiplet, SUN vector multiplet, here with a circle, and these are the fields in the vector multiplet. And I have here n fundamental matter fields. So I have this n is a flavor, and I have here these chiral fields indicated by the solid arrow. And if I want to include also their anti-chiral explicitly, I draw them by this dashed line, as I said. Now we distinguish between fundamental and anti-fundamental fields. So in this case, I have n fundamentals and n tilde anti-fundamentals. And if I include the anti-chiral fields, so these would be the anti-chirals of the fundamental, which are actually in the anti-fundamental, I have this picture. For ABJM theory, I have this picture where I have two pairs of bifundamental, a pair of bifundamentals, a pair of anti-bifundamentals. And in the doubled picture, it looks like this. If you want to write it in terms of n equals 4 language, you would pair one of these arrows and one of these arrows into hypermultiplets. And just to show that you can do more things, here is a 4-node n equals 2 circular quiver. If I wanted it to be an n equals 4 quiver, I would add these solid arrows. And if I include the anti-chiral fields and I want it to be an n equals 4 supersymmetry, I would have to double the dashed arrows on this figure as well. So these are the kinds of theories that I will study. And now I want to write the Wilson loops for them. And the simplest Wilson loop that you can always write in any gauge theory involves the vector multiplet, and indeed the simplest one involves only the usual vector field, and we have the path-ordered exponential of the gauge field along a closed contour, which I said in our case is a circle. And such a Wilson loop is not BPS. If you want to make it BPS, and you're working in this n equal 2 formalism, where your vector multiplet has also this auxiliary field sigma, then this combination of IA plus sigma is annihilated by some of the supercharges. This loop is 1/2 BPS in n equal 2 language. And this means if my theory is conformal, the vacuum has 8 real supercharges and the Wilson loop preserves 4. The story of this talk is really about Wilson loops that couple to chiral fields. And the story was developed by many, many people. And they exist now for all theories with n between 2, as I'm discussing here, and also going to ABJM theory and so on. In previous constructions, the matter fields were always assumed to be in the bifundamental representation of 2 gauge groups, but as I will show you, it's actually possible to use fundamentals and adjoints. So in this talk, so let me start with a case of fundamental fields. And let me take the Wilson loop that I had before and rewrite it in a very peculiar way. So I had previously the connection IA plus sigma. I rewrite it here again. I add to it a shift by 1 over 2r, where r is the radius of my 3 sphere. And I just put it into this larger block, where here I have an n by n block to include this gauge field, SUN gauge field. And I add here another 1 by 1 block and these n by 1 and 1 by n blocks into this object L0, which is actually an element of I will view it as a super connection. And then I take the super trace of the path ordered exponential of this thing. Now, of course, this is all zeros. So the only interesting part would come from here. If I take once I integrate around the circle, this 1 over 2r, and the circumference 2 pi r will give me a pi. I have e to the I pi, that will give me a -1. So this -1 together with this -1 will give me back my original w. And this block with this -1 and the super trace will give me a +1. So by using this extra structure, I calculate roughly the same Wilson loop. There is this +1 to it, but I'm going to ignore this distinction. I'm going to think of it as essentially the same operator. In any case, this is the one I'm going to be using from now on. And now, if I have n fundamental chiral multiplets, so I'm not adding any other vector fields, just chiral fundamental matter, I can add this block to this. And here I'm including phi bar. Phi is in the fundamental, phi bar is in the anti-fundamental. So this combination is an adjoint of a SUN. The combination here is in the other order. It's a fundamental of SUN. So it fits in a 1 by 1 block of this large n+1 times n+1 matrix. And the fundamental fields themselves appear in the off-diagonal. These u's and u bars are some arbitrary n vectors. They're not fields, they're just parameters. So this combination, as I explained, this is transforms in the adjoint of UN. This is in the fundamental and so on. This all fits, as far as group theory is concerned, into this one big matrix, and I can take the path ordered exponential of it. So I have my usual gauge invariance. This is a nice gauge invariant object in my theory, but it is actually also still supersymmetric. With these, so for that I need to include these particular combinations, and u bar appearing the same here and so on. Let me explain what this is in a picture. So we started with a theory which had the quiver diagram and one arrow and little n flavors. I rewrote here my connection L, and I will express this Wilson loop in terms of this quiver diagram. Now, compared to this picture, I did two things. First, I added the dashed line because I'm including also here explicitly these anti-chiral components of the field. So I want to be explicit about that. The other thing I did, I made this circle wiggly. And this is to illustrate this shift that I had to put here, which I didn't explain why, but I do have to do it to keep supersymmetry. And then what is this object? So this is a Wilson loop including both a gauge field and here essentially just the matter. There is no gauge field associated to it. So what you should think about is that you have here, if I expand this object to some order, so let me expand in particular in the order and the insertions of the fermions. I would have to have an even number of insertions of fermions alternating between psi and psi bar and psi and psi bar and so on. And between psi bar and psi, I have a connection in SUN. I have an open Wilson line in this block. After I put down a psi, I'm switching and I'm living in this block. So this light green regions only see this block. There is no gauge field here. There's just a combination of scalars. So this Wilson line is a combination of these open Wilson lines plus these open trivial Wilson lines here. Of course, just these things on their own, if I start with psi bar, a Wilson line and a psi, this combination is gauge invariant. But this combination, including all these terms and summing over any number of insertions of psi, will be supersymmetric. So these are the kinds of objects that I study. Generally, I can also gauge this block. But the new thing is that I'm not necessarily gauging it.
So which property determine the rank of the matrix you could call?
The rank of this matrix?
Yes.
I determine it. I have the freedom to choose different ranks. Okay. So one thing I didn't describe in this picture, which will be important, so of course what I had here, I started with this block, which is n by n, which I'm actually not I'm not specifying this picture. You cannot see it. So everywhere I'm ignoring the fact that this is an n by n matrix, and I will actually view it as one block of this gauge field and one block of these matter fields. But the fact that I put here a 1 means that I have only one block like this. And I could include more of these blocks and have a higher rank matrix. And this is a generalization that I will get to. And it's important. I'm not sure that that was your question.
Yes. Yes.
So the check of supersymmetry is technical. It's not as involved as in these particular examples that had these complicated Ansätze, because we can do it in one step. So what I do is I start with two matrices, G and G bar, which include in them the scalar fields and the chiral multiplet, phi and phi bar, and these extra parameters, the couplings U. And I take the sum of these two matrices, and now I evaluate what is the action of the acting twice with the supersymmetry on this G. Now, this, I said that we started with a vector Wilson loop, which is supersymmetric. So I combine its supercharges into a pair Q plus minus, and here I'm using Q plus squared, and it's a combination that is non-trivial. And just on the level of algebra, you can see that Q plus squared will close into a rotation. But if you check how it acts on these fields, the exact field realization of these Q in the off-shell supersymmetry, you get an extra term, which is the commutator of L naught with this curly G. Now remember, L naught included this piece in it. So we have here L naught, which sort of sits in this block, commuted with these G's, and this factor of 1/2R in L naught is important here because it acts on, you get it, it just appears in the supersymmetry variation of phi, but with an opposite sign for phi and for phi bar. So that's why I needed this shift of 1/2 here, which acts with a plus on this and with a minus on that one. And that's why this combination into a larger block makes sense. Now, we can write our new connection, which I wrote before in this form, as L naught plus this curly G squared. That will give me these terms, and a single action of Q on G, which will change the phi into some fermion and the phi bar into another fermion. Now we have this relation of Q squared acting on G given here. So using that, if I write Q acting on this guy, I can massage it into a covariant derivative with this connection. So here I had a derivative and a connection with L naught. Here I modified it to a derivative with a phi and this combination with which is this new L. So the variation does not vanish, but it is a total derivative, and that is enough to show supersymmetry because I have this variation inside my Wilson loop, and I can integrate it along the Wilson loop, and there are no boundary terms. So Q of L is different from 0, but it integrates inside the loop to 0. So that's how I prove supersymmetry under Q plus by explicit construction. We had another supercharge, Q minus, but it acts slightly differently on the chiral fields and the anti-chiral fields. So on the chiral component, it gives me a minus. On the anti-chiral component, it acts exactly in the same way. So the square of and likewise on the squares, it acts both on them with a minus. But now when I try to act with Q minus on my new connection, so I define my connection in the same way in terms of Q plus, but now I will need to act with Q minus on it. So I have Q minus acting on Q plus on G. And now some terms don't cancel. So I'm going to have still a covariant derivative of G minus G, but then all these terms. So in order for this to be a total derivative, I just need to keep this term. And therefore, I want to demand that G squared and G bar squared are equal to 0. So all these terms cancel. So this is why I split here my curly G into the chiral and anti-chiral part. And here you can see that these two G's both squared to 0. So I am invariant under Q minus, but if I take a G that doesn't square to 0, I will be invariant only under G plus, and I will preserve half of the supersymmetries as before. So I will consider both of these possibilities in what comes now. So we had the Wilson loop based on this, for this gauge theory with this quiver diagram. And now I want to add anti-fundamental chirals. And so I will construct this a n plus 2 times n plus 2 block, where this block is as before. It involves these fields, but the block up here involves these fields. And the fact that I had here a shift of 0, here a shift of 1 over 2r, tells me that here I need a shift of 1 over r. And then I can place the chiral fields here in G. So these fields are phi, and these fields are phi tilde. And here I have the anti-chirals. But you see that G and G bar do not square to 0. So this will result in Wilson loops that are 1/4 BPS. They'll be invariant under Q plus if I construct them with Q plus, but not under Q minus. We can do something else, and that is act with a gauge transformation, which eliminates this 1 over r piece here. So I wrote here explicitly what this gauge transformation is on these fields. And it introduced an explicit phase along the circle, but now this field behaves, so I start with a field here, and then it transforms under everything in the same way as this one. So I can actually, here, at this level, it's just a gauge transformation. I multiply it here. But now since this block and this block look similar, I can identify this row, these two columns, and these two rows, which means that I move this guy to here, and I move this guy to here, and I get these versions of G and G bar. And again, they don't square to 0, but that is fine. They didn't square to 0 previously. So here you have another way. So this is how I construct a Wilson loop with both fundamentals and anti-fundamentals. If I wanted a half BPS loop, I would have to either restrict to this side of the quiver or to this side of the quiver, meaning I need to restrict to this subblock or to this subblock of this matrix. So this was the construction. Now I want to understand what are the parameters appearing in it. So in our simplest examples, we had the parameters U and U bar, which are not complex conjugates, and they form 2n complex parameters. So it seems like I have a moduli space with a C to the 2n. But in fact, there is an extra gauge symmetry, which is not part of SUN, and that is the symmetry of multiplying L from the left and the right by this matrix that I have here. The Wilson loop is a product of these L's. So in every product, once I take the trace and so on, this X will disappear. And if you see how this acts on the U's, the U I had on the diagonal, I had a combination of a U bar that would be invariant, but here on the off diagonal, these U's would be scaled by either X or 1 over X. So it changes the loop with a UU bar into a loop with XU, or in U bar over X. So I'm acting on this, I'm modding out this C to the 2n by 1 C star parameterized by this X, acting by multiplication, division on the 2 copies of these C to the n. Now, this quotient is a bit subtle. You need to worry about what happens, say, when U bar is equal to 0. Then you get a block of this form, and then this scales with, this will scale with X. And but you can actually see that this object, once you multiply all these L's with each other and take the trace, this piece will never appear. So it does not depend on U at all. So if U bar is equal to 0 and U is different from 0, that is the same as U equals 0 and U bar equals 0. So when you take these quotients, which are not exactly manifolds naively, well, strictly speaking, what we need to do is identify all the singular orbits with the origin and get a nice conical space.
Is this double slash hypercilium quotient or something?
So it would be, if I had a way to impose extra supersymmetry, this would be the same as the hyperkähler quotient. Indeed, it's very similar to it. So this is the GIT a quotient in that with enough supersymmetry, which I don't always have, will give me a hyperkähler space. Yeah. But it's the same kind of quotient. So let me look at examples of moduli space. So in the case where I had a gauge field of any rank and one fundamental field, I have here one U associated to this arrow and one U bar. So I have a moduli space which starts off as a C squared, but I mod out by 1 C star, so I end up with a moduli space which is C. If I have two fundamental fields, then here I have a U1, U2, U1 bar, U2 bar. So I have 4. So I have a C4 mod C star. So I end up with a 3-dimensional complex manifold. And actually a simple way to see it, what this is to write these bilinears of the U bars, P, R, S, T, and they satisfy that they are, this product of them is equal to 0 by construction. So I can also write them as a matrix P, S, T, which of course is equal to the whatever it is, U1, U2, U1 bar, 2 bar. Maybe I got it a bit wrong. So what we have here is the space of rank 1 complex matrices, and that is the conifold. So we found here that the moduli space is the conifold, and for n greater or equal to 2, this would be the n by n complex rank 1 matrices, that moduli space, which is known. So yeah, to this, sorry, I need an extra line, but yeah, this is not hyperkähler because it's 3 complex dimensional, but it's a similar construction. Now here I assumed that this node is ungauged, so I could take any number there, If it's gauged, then I need to put the same U and U bar here to not break a gauge symmetry, and in that case of a SUN cross SUN gauge symmetry, I reduce again to 1C as the moduli space. In ABJM theory, I have more matter fields. So here is the picture with just the chiral fields. Here is the picture with the anti-chiral fields as well. And if I restrict just to the chirals and just to this pair of fields here, I get this Wilson loop. And the number of parameters are again 2 U's, 2 U bars. So again, we get the conifold. Now note that this is the space of 1/6 BPS Wilson loops in ABJM theory. If I included all of these lines in this picture, I would violate the condition that G squared is 0. So I would get 1/12 BPS loop and a larger moduli space. This would be, here I have so that would be a 7 complex dimensional moduli space of 1/12 BPS Wilson loops. I can generalize it further. So for example, here in the 1/6 BPS Wilson loops of ABJM theory, if I take 2 copies of one gauge group and 1 copy of the other, here I have 1 gauge group with a shift corresponding to this, and 2 copies of the other gauge group. It's the same gauge group appearing twice in this matrix. So I write it here with a 2. I have this structure of L, this structure of G and G bar. They still square to 0. And now, instead of the C star action, I have a GL2 action on this 2x2 block. So now the quotient that I have is a C, in this case, a C6 of P is 1, Q is 2, and modded out by a GL2. So I can construct all these moduli spaces as these quotients. I am out of time, so let me, I think I started 5 minutes in. So let me just finish with this graph. So the description that I gave you of the moduli space is actually what mathematicians would call quiver varieties, as defined by Nakajima, but used in physics mainly by Fanoni and Witten. So all of these spaces are quiver varieties, where you take a quiver and you assign integers to each node, which corresponds to the dimension of a vector space, and the arrows are linear maps between them. In our case, the linear maps are these parameters U and U bar, which are P times Q rectangular matrices. So they are linear maps between CP and CQ. This quotient that I took is gauge symmetry that mathematicians also want to take to identify inequivalent maps between these vector spaces. In this story, the rank of the gauge group plays no role. What is important is the multiplicity that I have. How many times do I write the same gauge field on the diagonal of this matrix? And that would correspond to these ranks P and Q that are in the representation of a quiver that mathematicians define. So in this way, I mapped the problem of classifying Wilson loop to the classification of quiver varieties. And this way, I can construct the moduli space. And here is an example of what I have if I have a single vector multiplet and a single adjoint chiral. So I start with this, a quiver gauge theory, but there is no way of shifting or unshifting this node in such a way that the endpoints of this chiral arrow go between a shifted and unshifted gauge field, unless I double this node. So I take two copies of this gauge field, one with a shift and one without a shift, and now my adjoint behaves as if it's a fundamental. And then I can say, take this one, couple only to this one, and I can get a 1/2 BPS Wilson loop in this theory, which was previously not described for this work. So let me ignore the case of n equals 4, which is in my upcoming paper. You can read it later this week or next week. And let me conclude. So what I found is an organization principle of BPS Wilson loops in 3D Chern-Simons theories. And I found an exact map to that of the representations of quivers and quiver varieties. This description is beautiful on its own. It probably has some deeper meaning that I don't understand, but just writing it in this language and eliminating all the big matrices and ansatz that were used previously, I found a few more examples that were not noticed before. I can implement localization, but all these Wilson loops have the same vevs. The chiral drops out, so they don't depend on where I am in the moduli space. So that's a bit boring. So some open questions. Is this an exhaustive list of all supersymmetric Wilson loops? I think the answer to that is no. And hopefully I'm going to have a paper soon discussing some extra examples. How is this related to the fact that quiver varieties also appeared in Harani-Witten in the construction of the moduli space of vacuum of n equals 3 theories? That I have no idea. The geometries that I had in all these cases where I took the quotients, I got cones. Is there a way to deform the cone or resolve the cone? Are these moduli spaces rigid, or do they get quantum corrections? And more generally, what is the space of the defect CFT? And I think these people started to think in that direction. And what about things like vortex loop operators? How does their classification arise in here? And if we have more supersymmetry also, what are the holographic duals of all these Wilson loops? I think that the recent classification of the Argentina group does not cover all of the examples. So this is what I have had to say. I'm sorry for running over time. Thank you very much.
Are there any questions from the audience?
Yeah, so our question may be related to some of the open questions you missed, but I really wonder, you know, for the gauge theory itself, like say Giotto using this quiver diagram to give very simple explanation of all those dualities, like S dualities. So if you could formulate the Wilson loop in that way, can you see the kind of dualities or any organization principle? Yeah.
Right.
Different...
So, okay. So here I was talking about n equals 2 and 3 dimensions, which is n equals 1 and 4 dimensions. So the classification, so these are not related directly to class S theories. Now, I mean, I wrote a completely different story on the classification of line operators in class S theories and curves on Riemann surfaces. A paper with Okuda and Dave Morrison many years ago, but that.
Yeah, but even for 4 dimension n=1, I guess quite recently people like this Schlommer or
Right.
Bruce's work, they're trying to think there's quite a similar picture.
That's right. So I guess the question would be, is there a notion of a generalization of the quiver variety to a generalized quiver, which is related to the Gayotto curve?
I see.
So, I mean, right, so, okay, and the simplest thing you do there is add a TN theory.
Mm-hmm.
Which should be something like that in our picture. So that corresponds, so the TN theory is tri-fundamental matter, effectively. And the story of when mathematicians talk about quiver varieties, they talk about linear maps. So you have, like, in a regular quiver, you have this picture. And mathematicians would think about it as a linear map from CP to CQ. And if you want to go to a Gayotto generalized quiver, you need to think of what is the analog in this language of a generalized quiver. And I'm thinking now, what is the analog of Hanani-Witten? So,
right.
So, I mean, forget about the story of Wilson loops, which is, what would Ami say if I asked him what is the what is the I can ask him, sure. What is the brain picture associated to and does it have yeah, so okay, my answer is that you should ask Ami.
Are there any other questions? I wonder if
oh, so you don't see my sorry, I'm writing on the slides and you don't, do you see them?
No, we didn't see that. So we see the final slides.
Yeah,
frozen.
the end. We are seeing the end.
It's frozen now. Okay, but the other writing, did you see it?
No.
During the talk, you wrote something and we can see it.
You could see it. Okay, good. Now my slides are frozen again, so let me unshare. I can share it. The picture I drew was stupid.
I see. Now you see it.
Right. So I wonder if you can uplift these line operators to 4D, for instance.
Yeah, I am thinking about it. I'm thinking about it. It's not obvious, so it's not conformal. So one of the nice things that happens in 3 dimensions is that the canonical dimensions for the fermions is 1 and for the scalar is 1/2. So bilinear of the scalars has dimension 1 and the fermion has dimension 1, so they all sit very nicely in this connection. How that works in 4 dimensions, I don't know.
Okay. All right. If there's no other further questions, let's thank the speaker again.
Okay, let's thank the
And
speakers.
all the speakers and all the chairs and all the audiences, participants.
Yeah, I think we should also thank Jan, the organizer
Thank
of
you.
this workshop.